Hi everyone, my name is Ariadna Sánchez and today I'm going to present my terminal project titled The Dynamics of HIV Infection in Lymph Nodes, a graph theory approach. The project I work on with Dr. Julian Alberto Fresan Figueroa and Dr. Ana Paulina Figueroa Gutierrez. First, I will explain how the presentation is divided. We will start with a brief introduction, then we will look at the model we use for this project, along with an example of the same and its demonstrations. Posterior to that, we will review the results and finish with the conclusions. Now, let's start with the introduction. We all know what HIV is, right? HIV is a virus that attacks CD4 cells, which are a type of white blood cell, which are vital for us to live and not get sick. And although there is currently no cure for HIV, there are several treatments that allow us to live with it and not infect other people. I'm going to briefly explain the virus life cycle. The first thing the virus does is reach a host cell. It converts the viral RNA into DNA. Then it integrates into the nucleus and performs multiplication. Finally, it does assembly and release. The curious thing is that this process rarely occurs in the blood, since only about 2% of CD4 cells are found in the blood. Therefore, it is said that the vast majority of the infection occurs in the lymph nodes, as this is where the cells are densely clustered. These are usually modeled as 2 or 3-dimensional square lattices. Let's move on to the model. Simon Monquemi proposed a graph-based model where the behavior of the virus in the lymph nodes is observed in different shapes. Let's look at some basic concepts. In the model, Monquemi tells us that the healthy birds will be color blue, uninfected birds will be red, and a dead bird will be black. Let's continue with the model rules. The first rule says that if a healthy vertex has at least one infected neighbor, then in the next time step, this vertex will become infected. The second rule determines that if we have an infected vertex, in the next step it will be dead. The third rule says that if a dead vertex has R or more neighbors, in the next time step it will become infected again. Otherwise, it will become healthy. A condition of the model is that at our initial time t equals 0, there will only be healthy and infected vertices. Let's look at an example. We have the following graph of 5 vertices with 3 healthy vertices and 2 infected ones. By rule 2, we can say that the vertices that are initially infected in the next time step will be dead. On the other hand, the vertices that are healthy have at least one infected neighbor, and by rule number 1, in the next time step, these vertices will become infected. Now let's analyze our time t equal 1. We know that the infected vertex in the next time step will be dead. But among the dead vertex, we observe that there is one dead vertex that has 3 infected neighbors, and since our constant r in this case is equal to 3, then this vertex will be infected in the next time step. Conversely, in or other vertex that only has two infected neighbors, and since this is less than or constant, then in the next time step it will become Hadley. Let's look at our second time step. Again, it's easy to see that our infected vertex will become dead in the next time step. But now there is no dead vertex that has 3 or more infected neighbors, and therefore these vertices will come Hadley in the next time step. And our only Hadley vertex only has 2 dead neighbors, which does not affect our Hadley vertex, and therefore it will remain so in our next time step. At t equal 3, we see that most of the vertices are already Hadley, and only one dead vertex remains, since there are no longer any infected vertices that can alter the behavior of these vertices. Automatically in the next time step, all vertices will be Hadley, thus ending the disease. So we can ask ourselves if this behavior always happens. That is, can it always be cured? Or does a value of R exist for which, no matter the initial condition, it will always be cured? Let's look at Mankiewicz theorem, which says let n be the order of a graph G. If R is equal to n minus 1, then the disease is cured. Let's move on to the proof of this theorem. Mankiewicz performs this proof in 5 cases, which we will see next. The first case is where there is no vertex of degree n minus 1. In this example, we have a cycle of 8 vertices, and therefore our constant R will be equal to 7. I decide to arrange this graph in this way to better visualize the behavior. So we can observe that this is the initial time. Applying the previously rules in our subsequent times, we will have the following. This is the state at t equal 1, at t equal 2, at t equal 3, and at t equal 4. We can see that the disease is extinguished. In the next case, we have the existence of a vertex of degree n minus 1, and this is the only infected one. We observe that in this graph we have 8 vertices, so R is equal to 7. It is easy to see that for the next time step the infected vertex will become dead, and thus that where Hadley will become infected. Now, since the dead vertex has exactly 7 infected neighbors, in the next time step it will become infected, and the infected ones will become dead again. At t equal 2, we see that the dead vertices only have 1 infected neighbor. Therefore, they will become Hadley in the next time step, and the infected vertex will die. So for t equal 3, we no longer have any infected vertices that alter the behavior of the others, and therefore in the next time step all vertices will be Hadley. Let's continue with the case where the vertex of degree n minus 1 is not the only infected one. Again, we have a graph with 8 vertices and R is equal to 7. We have this initial state with the top vertices infected and the bottom ones Hadley. In the next time step, the top ones will die and the bottom ones will become infected. Then, the bottom ones that were infected will become dead and the top ones will become Hadley. Since we no longer have infected vertices affecting the others, In the next time step, all the vertices will be Hadley. Now, we have the case when there is a vertex of degree n-1, it is Hadley, and e is equal 1. The constant e is the maximum distance from a Hadley vertex to an infected one. In this example, we have a graph of 6 vertices and r is equal to 5, where the vertices on the left are Hadley and those on the right are infected. In the next time step, the Hadley ones will become infected and the infected ones will die. Then, the ones on the left that were infected will die and the ones on the right will become Hadley. Finally, the disease will extinguish. In our last case, we have that there is a vertex of degree n-1, it is Hadley, and e is equal to. We have 9 vertices and r is equal to 8. We can observe again that in this case, as the time progresses, the graph leads to a time when the disease is cured. We define HIV of G has the minimum R such that for any initial configuration the disease extinguishes in the Moncoin-Vince model. Therefore, HIV of G will be less than or equal to n-1. Let's move on to the results we obtained, which were found through the implementation of a program that simulates the model. So this is how we found the values of HIV of G for the following types of families: complete graphs, cycles, paths, wells, star, complete bipartite graphs, and grids. This is the table with the results for the first 5 families we mentioned, and based on this, we arrive at the following theorems for each one. In the table for the complete bipartite graphs, due to their structural symmetry, it is sufficient to consider the case where n is more than or equal to m, since swapping the partition does not alter the behavior of the model or the value of the HIV number. Therefore, we arrive at the following theorem. A similar behavior occurs in grids, where it is sufficient to consider the case where n is more than or equal to m. Unfortunately, we could not obtain all the values, as there are too many initial cases. However, with the few results, we were able to conclude the following theorem. Let's look in more detail at the theorem for HIV number in stars, which states that it will be 2 if n is equal 1. Otherwise, it will be the ceiling of the quantity n plus y divided by 2. Let's proceed to the proof of this theorem. First, we know that the only vertex that has more than one neighbor is the center. Thanks to this, we can rearrange any star in the following way, where we put all the hated vertices on one side and the infected ones on the other side. So, we denote A has the set of all external vertices that are initial Hadley, and B has the set of all external vertices that are initial infected, while C is the central vertex. For the proof of the theorem, 5 cases arose, the first 3 of which, with all their subcases, we can see on this slide. On this other slide, we have the 4th case, also with all its subcases. Then we have case 5, and again with its subcases, but subcase 5 and 6 still have more cases that we have observed on this slide. Since there are several cases, I will only explain the realization of 2 of them. Let's start with case 3.6, which says that if we have two external vertices and R is more than or equal to the ceiling of the quantity n plus 1 divided by 2, and we have an initial state where the central vertex is infected and external vertex is healthy and the other is infected. In the next time step, the vertices that were infected will become dead and the vertex that has healthy will become infected because it had at least one infected neighbor. Next, the vertex that was infected will become dead again, and the vertices that were dead will become healthy because they don't have a sufficient number of infected neighbors. Finally, at time t equal 3, the disease is cured. Now let's look at more complex cases. In this case, we have n is more than or equal to 3, and R is more than or equal to the ceiling of the quantity n plus 1 divided by 2. We have an initial state where the center is healthy. We have a quantity of the ceiling of n divided by 2 external vertices that are initial healthy and the rest are infected. In the next time step of the center will become infected since it was more than one infected neighbor, and those that were infected will become dead, while the remaining external vertices that were healthy will remain in that state since they didn't have infected neighbors. In the second time step, the center will become dead, the vertices that were dead will become healthy since they only had one infected neighbor, and those that were healthy will become infected since they had at least one infected neighbor, which was the center. Let's look more closely at stage 2. We know that the ceiling of n plus 1 over 2 is greater than or equal to the ceiling of n over 2. Let's look at the case where they are equal. Then, in our next time step, the center will become infected again since it has R infected neighbors. Those that were infected will become dead and the healthy ones will remain healthy. In the next time step, the center will die. The external vertices that were dead will become healthy since they only had one infected neighbor, and those that were healthy will become infected since they had an infected neighbor, which was the center. Let's look closely at this last time step. We know that n minus the ceiling of n over 2 is less than or equal to the ceiling of n over 2. In this case, we will look at the one it is less. Then, for time t equal 5, we will have that the center will become healthy, since it didn't have a sufficient number of infected neighbors to become infected again. And our external vertices that were infected will become dead, and the healthy ones will remain healthy. Finally, at time t equals 6, all vertices will be healthy, putting an end to the disease. We solve all the other cases in the same way, but due to the time constraints, I will not be able to explain them. In conclusion, we can say that the geometry of lymph nodes is known, but at least this version models it in a more general way, where it is deduced that the probability of a dead cell being replaced by a healthy one is 1, and thus the disease is cured. That is all for me. Thank you very much for your attention. I hope you like the presentation of my terminal project. See you soon.